In this video, we will implement ESRGAN from scratch, and I highly recommend you to check out both the SRGAN and then the ESRGAN paper walkthrough, because in this one, I won't be explaining how ESRGAN works, but I will try to go through how to actually implement it. So, and also what I want to do is to focus on the model architecture, right? So we've done multiple videos where we go through the training setup for GANs, and I don't want to repeat the same process. So if you want to see that, I'm going to refer you to the previous videos. I'm going to step you through the model, then I will copy over the training setup. I will go through the training setup so that everything kind of makes sense. But I won't code it from scratch because it just feels like it's unnecessary. So this is an image of the architecture where on the above here, right here, we see the sort of the ResNet architecture, SRGAN, and basically they replace the residual block with this we talked about in paper walkthrough of this this new residual block, which uses these dense blocks. And we saw that one dense block contains a bunch of conv layers. So it's much, much larger than the original SRGAN. Anyways, we're going to create the model. And this is sort of the difference, right? They did a relativistic GAN and stuff like that. But the main component was the model. And that is what we're going to focus on. All right, import torch. And let's see. Then from torch import nn. Shout out to Francesco for pointing out that you shouldn't do import torch.nn as nn, but instead from torch import nn. And I agree that it looks better. Anyways, we're going to create a com block. And the difference here is that this is not going to contain any batch norm. So here we're just going to send in some in channels to some out channels. We're also going to specify use activation and then some keyword arguments. We call super, and then we specify our conv layer and com2d of in channels to out channels, and then keyword argument. And we'll set bias to true. I guess it's by default, but let's just be clear. We're going to set bias to true because we are not going to use batch norm. So, and then the self.activation is nn.leakyRelu 0.2 in place equals true. If use activation, otherwise we're going to do nn.identity. And I guess you can also do an if statement in the forward part, but I guess this is a simple way. Then we'll just do self.activation of self.cnn of x. And I'm doing this one quickly. I'm assuming that you've followed along with the previous videos. Okay, so then when we've done the com block, we're going to create an upsample block. And here it is, as I mentioned in the walkthrough, it's going to be a little bit different in the way that we're going to use nearest neighbor upsampling instead of pixel shuffle. I'm not sure why they did that, but it's what I found to be the case in the source code. So we'll do in channels and then scale factor. And one thing I also want to mention is that I won't train this. It just takes too long, and honestly, I don't have that much trust in this paper and its implementation. I feel like there are details that could just be super annoying to debug. What I will do, however, is that I've taken the weights, the official pre-trained weights that they have. I've sort of taken them so you can import them into this model. So there is available to have sort of pre-trained weights, but I'm not going to show you or train it in this video. I'm just going to show you how to implement it. Okay, so we want to create the upsample block, and as I said, they do a little bit differently in the way that, they use nearest neighbor upsample. So we just do nn upsample. We specify the scale factor to be scale factor. It's always going to be 2. Perhaps we can specify that. So it's going to double the height and the width. And then I think mode nearest is default, but that is what they use, nearest neighbor upsampling. And then we're going to create the com2d, and here we don't change the channels anything. We just do in C to in C, kernel 1, stride 1, padding 1, bias true. and again activation to be and then leaky relu, and then in place true, just for some I guess it's a little bit faster to use in place equals true. All right, so then for the forward, this is just going to be self.activation, self.conv of x of, we also need to include the upsample, right? So self.upsample of x. Yeah. All right, so now we have the conv block, the upsample block. Now we'll create the dense residual block. So, you know, nothing has been difficult so far, hopefully. For the ESRGAN, we want to create this this residual block, right? But for that we need to create this block right here, and so I'm gonna create this block now, which I call the dense residual block, and then we'll see how to put it together to form this this one, and then lastly we'll see how to put that together to form the entire generator. So for the dense residual block, yeah, we're gonna do init. We're gonna have some in channels, and I'm also gonna specify channels here to be 32, and I'll explain that in a little bit. And then the residual beta, which is the residual connection, the constant parameter that we'll multiply with, which is going to be 0.2, that we saw, you know, in the paper walkthrough. Then for the residual beta, we'll just set it self.residual beta. And then we'll do some blocks, and we're gonna set that to modulist. Let's see, so self.module list. And the reason for this is why you would create this is when you want to do a for loop in your forward part, then it's a good idea to use modulist, because those parameters will then be maintained by PyTorch, the NN module, in case you want to do mod.eval and stuff like that. Yeah. All right. So then for I in range of 5, we'll do self.blocks.append, and here we'll do conv block. So we'll use the block that we created before. We'll do in channels, and the in channels will be in channels, and then it will also be plus channels times I. So the reason here why it's going to increase with channels times I is that, as you can see, we're sort of concatenating more and more and more as we go forward, right? So here we are actually concatenating the out from this one, from here, and from here. So there's going to be a lot of concatenation, and that's where these additional ones are included. So the first one doesn't have any, right? When we send this one, it doesn't actually concatenate anything. But the second one, right, that's when I is equal to 1, then that is our first concatenation. And the reason why I specify channels here and not in channels is because they actually change the number of channels. So they go from in channels, which I believe is 64, to out channels to be, all right, so I had to double check on this part. But yeah, they do it to channels, which is going to be 32. Unless it's the last one, right? So if I is 4, then it's not going to be channels. But so we will just do if I is less than or equal to 3. Otherwise, we'll set it to in channels. So it's going to be down. We're going to reduce the number of channels for all the ones except for the last one. So then the kernel size here is going to be 3, stride 1, padding 1. And we'll just specify also use activation is true. And this is the case if I is also less than 3. Otherwise, we're going to set it to false. And the details of this is from what I gather from the source code. And the reason why I know that this works and why it's correct is because I'm also able to load the pre-trained weights, right? So in that way, I know that it's sort of the exact same as they did it. So... all right, so that's the when we generate all the blocks. So then in the forward part, and you know, remember the tricky part here, I guess, would be that what is going on. So I guess here for the tricky part will be that we need to concatenate, right, for all of the different ones. So we need to concatenate the one from the first, and then so if we're at the end, for example, we need to concatenate from the first, the second, the third, all of them together. And so what we'll do is I'll specify new input to be x, and then I'll do for block in self.blocks. And again, this is why we use a module list, because we're iterating through it. Then we'll do out is block of new input, right? So this is just going to be x from the beginning, right? Then we'll do new input is torch concatenate of new input and out along the channels, which is dimension 1, because the first one is the examples in the batch. So this will be new inputs. It will be x in the beginning, and then it will be new inputs where we append the concatenation of out. So if you think about it, in the beginning, for the first block, it's going to add it. Then for the second block, right, it's going to add out from that one. And remember that new inputs is then including the output from the first one. So we're sort of just concatenating one block at a time. And then why we also specify these new inputs instead of just using x is because in the end here, we're going to do self.residual beta times out and then plus x, which is the skip connection. So one thing here is that this last new input is not going to be needed. So I guess this is a little bit unnecessary computation, but this makes it a lot cleaner, right? It's just 5 lines or whatever, so very, very compact. But so here we take the residual beta 0.2 and we multiply that with out, which, as I discussed sort of in the paper walkthrough, is that this feels a little bit odd where you would maintain the original one when we've done so much computation. But yeah, I guess it works. So, but it feels to me strange to do this. I would sort of rather do the opposite, that you would maintain a weaker signal of the previous ones rather than intuitively it doesn't make too much sense. All right, so then we'll create the RRDB, which is what I'll refer to be one of these residual blocks, right? So this is, what is it? Residual dense block. I don't know why I forget the abbreviation, but anyways, it's going to be this new residual block right here. Yeah, so this RRDB is going to be this right here to the left, where we'll have 3 of those dense blocks that we just created. And we'll try to put this all together. So here we'll do first the init method of in-channels, residual beta, and then call super on that. And we'll just specify the residual beta to be residual beta. And then we'll create the RRDB, which is going to be 3 of those blocks, right? So we'll just do an unsequential of asterisks for unwrapping all the ones that we're going to do, which is then residual block of in channels for underscore in range of 3, right? We want 3 of them. And then in the forward part, we'll just return self.rrdb of x, and then times the self.residual beta and plus x. So yeah, I mean, we're doing the same thing, right? Here we have the skip connection for that one after we've done all the ones, and the one intermediate here is what is done in the dense block. So these ones are done in the dense blocks, and then this is done afterwards, which is what we do over here. But that is the RRDB block, and yeah, so now what we want to do is we want to put this together for the generator. And so we'll do class generator. We'll create the init method, and we'll just specify in channels, or the sort of the image channels, which is going to be 3, the num channels, which is going to be 64, similar to ESRGAN. And then we'll specify the number of blocks, which is going to be 23, which is a lot of blocks. You know, just doing some quick maths on this. This network is, I guess, 10 times as many comb layers as the one for ESRGAN. And you kind of wonder if just the better results come from being 10 times more comb layers. Like, how much does these tricks that they use, like with the dense residual blocks and all of that stuff, how much does it actually matter when it's such a larger network? In many ways, it feels like an unfair comparison. But yeah, so we'll do in channels to the number of channels. So the initial that they did in the code is that they had an initial comb layer, which was just a com2d. It didn't have a leakerel or anything. So kernel size 3, stride 3, padding of 1. And this is different from ESRGAN, as mentioned previously, which is that they use a kernel size of 9 here. So this is also quite different. Then we'll do self-led residual. So self-led residuals here, let's see, this is going to be, all of these RRDB blocks. And it's going to be quite many of them. It's going to be 23 of them. So here I will just do unwrap RRDB of num channels for, underscore in range of num blocks. So you can kind of imagine that behind these self-led residuals, there's a lot of comb layers because we're creating 23 of them. All of them are creating 3 dense residual blocks. All dense residual blocks are creating 5 comb blocks. So there's a lot. All right, and then we'll do another comb layer. So this is similar to ESRGAN, I guess, in many ways. They were definitely inspired by that, at least. All right, so then we'll create another. So the NNCOM here will be just num channels to num channels. They're not changing the channels anything here, which is nice, similar to ESRGAN. I guess the difference here would be that the dense residual blocks are making the channels to 32, which is why we specify this. So it's not maintaining 64 all the way through, but after the residuals, it's at least going to be 64. So it's going to be maintained after all of the blocks. So that is one comb layer that we're going to have after, and then we'll have the upsamples. So the upsamples are going to be a NNCOM2D of, no, let's see. So the upsamples are just going to be our upsample block, right, that we just created. Upsample block of num channels, and then another upsample block. So the scale factor, perhaps we can specify those, but the scale factor is going to be 2 by default here. So we'll just have 2 upsample blocks, and similarly as ESRGAN here, we are doing all of the computation on the low resolution image, and then we're upsampling it at the end when we're sort of almost done, and then we do we're going to do the final, so to speak, and the final is just going to be a com2d of num channels to num channels 311, a leaky relu in between, and then another com2d, which is going to take num channels to in channels 311. And again, maybe we can, for clarity, we can do bias equals true. So that is the structure here. And, this is very similar to ESRGAN. We have some initial, we have some residuals, we have another com block, we have some upsamples, and then we have a final one. And so that, if you follow the other implementation, this is going to be very, very similar in the structure, although the details of it is very different, since we're using RRDB instead of just the residual block that we did then. The upsampling block is different because we did use pixel shuffle. Now we're using nearest neighbor upsampling. But so for the forward here, we're just going to run it through the initial. And here also they're using the same sort of skip connections as for ESRGAN. So we're going to just run it through the initial. Then we'll do self.residuals of initial. And then we'll do self.conv of that one. And then after that conv layer, we'll add initial. One thing I'm not really sure why there's no leaky relu in between there. So here, why there is no leaky relu here. That could be a mistake on my part, actually. I'm not sure about that, but I tried to replicate it as they did, so perhaps there is no leaky relu there. All right, so we do that, and then we'll upsample it. So we'll do self.upsamples of x, and then we'll return self.final of x. And that's it. So now we've done all the generator stuff, and we'll just create the discriminator. And I'm actually gonna this is gonna be exact same as we did previously. So I'm just gonna copy paste that in. So this is copy pasted as we did in ESRGAN. We specified the features here, very VGG like. We create the blocks by using COMBLOCK, where we use activation to true. The stride is going to be 1, 2, 1, 2, which is why we did this index modulus 2. And you can watch the ESRGAN video if you're completely new to this, but you know, this is what we did in that video. And then we'll do the blocks, and then we'll have a classifier at the end where we first do an adaptive average pooling to be 6, 6, because we want to be able to use different image sizes. So for 96 by 96, this is going to be 6 after we run it to the discriminator. But if we use 128 or 192, then it's still going to be average pooled to be 6 by 6 in the height and the width. And then we'll flatten, we'll do linear, leaky, and linear. And that is it for the discriminator. So pretty simple there. And then also one detail that they mentioned is that they initialize the weight. And I believe this is only the weights for the generator, but they initialize the weights of some model where they multiply each weight with a scale of 0.1. So they make the weight, they initialize the weight smaller. So, you know, to do that, we'll just do for m in model.modules, and we'll check if is instance m and then com2d. Then we'll do an chiming initialization, which is, I found this to be the case that they do in the source code. Perhaps it's also clear from the paper, but I missed this part. But they go through, so they do that in place of the weight of the com layer. And then we're going to do m.weight.data times equal with scale, which is 0.1. And we'll do the similar thing for the linear layer. So else if is instance m nn.linear, then we'll do the same thing. So maybe we can just put them two together, right? You can do that, I think, like this, and then linear. Hopefully you can do that. I think you can do that, but let's just do this because I know it works. But you can combine these into one if statement for sure. All right, so then I'll copy paste over a test case just to make sure that it runs, because now we've written a lot of code. So hopefully this will run and we'll see. So, you know, here I'm just initializing the, all right, so we're done, but here I'm initializing the generating discriminator. We have some low resolution, which is 24 by 24. And we're going to make sure that when we run it through the generator, we'll get back the 96 by 96. And yeah, for the discriminator, we'll get just a scalar value. Module torch.nn has no attribute module list. I think the module list should be with a capital. There we go. I think this should perhaps be with a capital L. Let's see if that's the case. All right, and that was the case. So that's nice. So no major mistakes, I think, here. All right, so as I mentioned, you know, I wanted to show you the model and how to set that up. But for the actual other stuff, we've done that many times, and I don't want to repeat stuff that we've done many times. But so for the loss, for example, we did this in the ESRGAN video. All that we're going to change is this. We had 36. Now we're going to change it to be after the ReLU activation. So that's up to 35. Then in the, let's see, we're also going to have a data set. Nothing really to focus on here. This is just so that I have basically created my own image folder so that I can specify the transformations to be done by albumentations. So, this is nothing difficult, nothing special here. You can probably use Torch Vision and just use image folder as well, but I just like using albumentations, so that's the reason here. And then let's see, for config, here we just specify sort of some basic stuff like the learning rate, number of epochs, batch size, lambda GP, the high resolution, which is 128 by 128 crops, and we specify the transformations, similar as we did in ESRGAN. This is exactly as we did for ESRGAN. And then in the utils file, we'll have gradient penalty, save, load checkpoint, and plot examples. This is just so that we specify a low resolution folder, and then it's going to upscale or upsample all of the images in that specific folder. And it will just go through the image file in that one. And then for training, one thing that I kind of cheated with is that instead of using this relativistic GAN, I just used vGAN GP because it's simpler. I really believe that vGAN GP will produce the same results. It might be a little bit computationally more expensive, but I think it'll bring the same results. Anyways, we just have our imports, and then we have a train function. We've done this many times, in these videos, but here we have vGAN GP setup, where we have gradient penalty and just loss of the critic. We have float 16 here. So, and then we have the generator. So I'm using the constants that they mentioned in the paper here, 1e minus 2 for L1, 5e minus 3 for the adversarial loss. You might have to tweak these constants a little bit, just because I'm using vGAN GP, the exact loss term might not be exactly the same. What I would suggest is just to run it, see what you get for the loss critic term, right, which you want to converge to 0 eventually. Just check. If it gets stuck for too long, I would decrease this adversarial loss slightly. And then also one thing that is very important to do is to pre-train the network so that we would uncomment the discriminator, we would uncomment these two, and only use the L1 loss and train that for, I believe it was 1 million update steps or something. So we would train it for a very long time. And then we would introduce the discriminator and train that with these constants right here. So that is how we would train it. And then, just some other stuff like writing to TensorBoard and sometimes plotting the examples to see how they look like. I guess this is a bad name, plot examples. It just saves the examples to a folder, but whatever. And then in the main we're just creating the data set loader. We're doing generate discriminator, initialize the weights. We create the optimizers. Here I'm using the beta terms for vGAN GP. So I'm not using 0.9 and 0.999. Although if I would pre-train this for L1, I would use 0.9 and then 0.999, just because the vGAN GP component is not involved with the generator then. So that is what I would do. And then here we're just doing initializing all the losses, the G-scaler, D-scaler for float 16, and we're loading the model if we have set the config to load the model. And then we're training for epoch in range of num epochs, and then every epoch we're also saving the model. All right, so that was a quick walkthrough. The source code is going to be on GitHub if you want more details on this, and I've also done it in previous videos where you can go through it. But what I want to show you now is so we're going to take those pre-trained weights that they had, And so I'm just going to take, so the generator, I'm going to copy paste that over. So it should appear here. That's the gen.pth, which is the pre-trained weights of the generator that from their implementation. I'm also going to put this on my GitHub. Probably, I think I'm allowed to do that. I'll just refer and say that, you know, this is their weights. I haven't trained this, but so we're gonna load that now just to see that it works, you know. And so maybe here we don't have to actually run the training now. So we'll just do plot examples of, let's specify it to be tests maybe, and we'll do the generator here. And then we'll do, so I've created another folder here, saved, which is where the high resolution upscaled images will be. And then I'm also gonna put over some test cases just so we can see that they look all right. So I'm gonna copy paste that over. Here we have the test images. So here we have this image, which is low resolution, which looks like this. And we have some other as well. So let us run it and see if it works. So this should be train. And here I just uncommented the loading of the discriminator because we don't have a discriminator. So we're not gonna load it because they didn't include the pre-trained weights for it. But so let's see. Now so we need to specify the data in some data folder. I haven't included that in this, but so maybe we can just for now comment out the data set since we're not actually going to train this. All right, so this should be test images like that. All right, so now we should have the high quality ones, and we don't. All right, so we didn't get very good quality images from the saved one. It looked like this. And the reason why we didn't get that good is because they didn't normalize the images to -1 to 1 that they did for ESRGAN. They actually normalized them to be between 0 and 1, which is just another thing that frustrates me. Like, that's not what they did in the ESRGAN. So, you know, they should be clear about those things as well. But yeah, so that is what they did. And let's see now if we get better results. All right, so now when we run it, and I also remove this I also remove this sort of conversion back to normalize it with multiplying by 0.5 and adding 0.5 to just be the upscaled image like that. And so if we look at the images now, they should hopefully be good. And that looks very good. So, you know, if we compare, this is what it looks like. And then the upscale looks like this, which is, you know, it's pretty incredible that it's able to do that. To be honest, that looks really insane. So let's see the other one. So this is the saved one. This is the test one. So let's see, this looks like this. Wow, that's a lot clearer as well. For sure, that's a lot clearer. Yeah, that's really good. And then the butterfly. Wow, that is such a big difference. Yeah, that is cool. Maybe if I get time some point, I'll also train it myself. But as I said, there's just so many details that I just think it would be a waste of time. Because I think there are details as well that you would find out if you really dig into the source code some more, some sort of key points. But I really think that, you know, the main ideas and everything is conveyed hopefully in this video. Perhaps not the relativistic GAN, but otherwise, you know, really the main parts and the model and the architecture and all of that stuff. And I'm also going to, you know, so, you know, you can download their weights and you can convert them, or I'm just going to upload the weights here to GitHub where you can download and you can play around with it if you want. But yeah, that is it for this video. Hopefully you thought it was useful. And yeah, just want to say thank you for watching and hope to see you in the next video.